Good morning, ladies and gentlemen. I'm so grateful to be here with you in the second National Conference on Applied Science and Advanced Materials. So, first of all, I'm going to present myself. My name is Benlembarek Sabrina. I am a PhD student from the Mechanical Engineering Department. Today, I'm going to present my work as a poster presentation. So, my title work is Effect of Back Pressure on the Flow Through a Supersonic Nozzle. So, first of all, we are talking about the nozzle shape. The most typical shape of rocket nozzles is the bell type, so that use pressure, energy, and fluid enthalpy to increases the out of the flow velocity and the direct of the flow in the gas produced by the combustion chamber. So the hot, pressurized gas passing through the nozzle is converted to supersonic due to the conversion of the heat energy into a kinetic energy. And in this work, I'm using the ANSYS Fluent software. We just use one half of the nozzle because of the symmetry reasons. And I choose for the analysis of the flow the K omega double ST turbulence model. And especially in this work, we study the influence of the back pressure. We use different ampere values. And in this work, we have a simulation extended to know the shocks and their behavior. So it is observed that the shock strength increases and the shock move towards to the exit of the nozzle with the increases of the ampere. Here we have some results with the discussions, the results of the pressure, the temperature, and the velocity. The contour of static pressure are in Pascal are depicted in the pictures. A typical shock wave ends this zone of supersonic flow. The pressure is raised by the shock wave as the back pressure is further reduced to the value of the and the shock wave moves further down the divergent portion of the nozzle toward the exit. The flow was decelerate subsonic, enter the pressure of the exit plane is equal the back pressure. And the contours of temperatures, the temperatures almost remains a constant from the inlet to the throat. Increase is observed after some distance from the throat towards the exit, as seen in the figures. The temperatures of the flow also increases. Increase of temperature, this is due to the physical nature of the fluid where the internal energy decreases to a lower level. The energy increases internal due to resistance they present due to the increases in the pressure. Consequently, the temperature increases, the sudden change of variation of magnitude of the temperature are present in the region where the shock occurs. And now we move to the velocity contours. We notice that the speed increases in a uniform way, and the speed at the level of the throat is equivalent to the speed of the sound, but the speed increases markedly after the throat for maximum speed. The speed increases from the nozzle inlet to the outlet where it reaches its critical value at the throat. The maximum supersonic at the nozzle is in the outlet. And now we have some conclusion like that. The initial inlet pressure and temperature were gradually reduced. The expansion of gases was constant inside the nozzle. The results obtained from the study are identical with the experimental results. The simulation using the standard turbulence model K omega double ST give more realistic values. When the flow is compressible, the flow velocity, the Mach number, the static pressure, and the static temperature can all vary from section to section when the flow is compressible. The study had processed to determine how characteristics of a fluid change with different ampere values. When the back pressure is nearly equal to the stagnation pressure, the flow remains subsonic throughout. As the back pressure decreases, so does the throw pressure, which is lower than the back pressure. And here we have some references that used in this work. And finally, hope you understand my work, and thank you so much for your attention.